All right, limit comparison test. I want to talk about that a bit. So first question is when to use. When to use it. When to use the limit comparison test. This is if you have a polynomial divided by a polynomial. Anytime the series is a fraction of polynomials, the limit comparison test is the ideal tool to use to check for convergence. Or if it is an algebraic divided by algebraic. Actually, this is a little bit more. Polynomial over polynomial is a subcategory of this, but I wanted to mention this. This is what occurs most often. This occurs at times. So this is a polynomial. This might involve square roots, or this might involve polynomials. This might involve square roots, or this might involve polynomials. So any mix of those would be a case where you could use the limit comparison test. So a specific case might be this. an is equal to the sum, n goes from 1 to infinity, and our sum is n plus 3 over, what do I have here? I have n to the 4th plus 2n. All right? So that's the series. It's a polynomial divided by a polynomial. There's a series. And we want to check to see, does this converge? So a test for convergence. So does this series converge? That's our question. That's what we want to find out. All right? We may apply the limit comparison test. So we get rid of this and show the procedure for how this is done. This is the series whose behavior we want to learn. We need to find a series against which to compare. So to find the series to use for comparison, and it actually is limit comparison. So what do we need? We need the limit of an over bn. An is what we want to find out. This is my an, the behavior we don't know, right? Here's how this is done. You look at the polynomials. You look at the numerator and the denominator. This could be a radical as well. Look at the numerator and denominator. Take the highest degree term. The term with highest degree is n to the first. In the denominator, take the term with the highest degree. In this case, n to the 4th. Everything after that, you may safely ignore. And so we need the series. We're going to use the series, sum, n goes from 1 to infinity. This is called the dominant term. This is called the dominant term. All right? The dominant term here is n. The dominant term here is n to the 4th. We may safe, as far as we're concerned, to find the series to compare with, you may ignore everything except the dominant term, everything except the dominant term. So n over n to the 4th, and when we simplify that, look what we get when you simplify this. It's 1 over n to the 3rd. This is a p-series. This is a p-series with p bigger than 1. A p-series with p bigger than 1, this converges. This is a series whose behavior we want to learn. This is a series whose behavior we know. This is the unknown series, A. This is the known series, this is B. And so if we form the limit of this unknown, limit as n goes to infinity, I need to form It's going to be a fraction of series. In fact, it's going to be a fraction of fractions. You almost always will form a complex fraction. The complex fraction in this case is n plus 3 over n to the 4th plus 2 over 1 over n cubed. And then simplify that expression and evaluate that limit. So this is the limit as n goes to infinity. This is multiplied by the reciprocal, right? Multiplied by the reciprocal. So this is n plus 3. The first time I'm going to show all my work here, this is basic algebra. This is n to the 4th plus 2 times 1 multiplied by the reciprocal. If you distribute, what you generate is n, or limit, as n goes to infinity, of n to the 4th plus 3n to the 3rd over n to the 4th plus 2n. I left my n off on this expression. And evaluate the limit of that expression. If that limit works out to be finite and positive, then they agree. They agree on what? Well, we know this one converges, so they would agree on convergence. If we had compared this to 1 over n to the 1/3 power and is finite and positive, then they would agree with what that behavior is. If this is n to the 1/3 power, this diverges, and if they agree, then the unknown series would diverge. In this case, I'm going to run out of space, but I'm going to leave it to you. You can verify. Divide every term that appears by n to the 4th. We're going to get a short version here in just a moment. We're going to divide every term that appears by n to the 4th, and you're going to get 1 plus 3 over n squared over 1 plus 2 over n to the 3rd. If you do the algebra, that goes to 0, that goes to 0. This is equal to 1. And so I'm going to steal some space over here. So we may say, what do we conclude? Remember, the limit comparison test, the conclusion is not that it converges. The conclusion is not that it diverges. The limit comparison test, the conclusion is, therefore, they agree. It is never, ever, never, never, ever, it's never, ever correct to say the limit comparison test, you say, therefore, it converges. That's not right. The conclusion of the limit comparison test is never converging or diverging. The conclusion of the limit comparison test is they agree. All right? They agree. Now what we need to do is say, well, what do they agree on? They agree on, we knew this was a p-series that I've erased it here. This is a p-series that converges. Therefore, the series n equals 1 to infinity of, I need a summation here, n plus 3 over n to the 4th plus 2n converges. All right. So that takes a lot more time if you explain it while you're doing it. If you don't need to explain while you're doing it and you had a little bit bigger chalkboard, it would be a little bit more straightforward. So what I'm going to do now is also, on the next examples here, we'll go through several cases and work through several instances of the limit comparison test. And I think it's not very challenging to get the hang for how this works.